Good morning, students. Today we are going to discuss a topic from fluid mechanics. This topic is very important because every time one question, which is of 1 mark or 2 mark, has been asked for the GATE exams. So this topic is from flow through pipes, and the name of the topic is major laws. Okay, so before going to the topic or before going to discuss about major laws, let's say some of the assumptions we are considering in this scenario. Okay, so when we write the Reynolds number or when we write the equation of Reynolds number, we know that for a pipe flow, the equation of Reynolds number is rho V d by mu, where rho is the density of the fluid, V is the velocity of flow, d is the diameter of the pipe, and mu is the viscosity, or to be specific, it is dynamic viscosity. And remember, this equation is only used in case of pipe flow only for pipe flow. Okay, when we come to what we say that when we come to open channel flow, the equation also changes. When we think about or when we consider about boundary layer theory, also this equation changes. So remember, this equation is only for and flow through pipes. Okay, so now let's say something. So when the Reynolds number is less than 2000, we all know that. When the Reynolds number is less than 2000, the flow is laminar, and when the Reynolds number value become greater than 4000, it is considered as to be a turbulent flow. Okay, and any value in between 2000 and 4000 is considered as transition. So remember, for flow to be laminar, it should be less than 2000, which means it can come to a maximum of 1999. And as well as for the flow to be turbulent, it should be greater than 4000, which means the minimum value starts from 4001. Which means whenever you find the Reynolds number value and if you get a value of 2000 or 4000, the flow will be transition, not laminar or turbulent. Remember, okay, whenever this value is less than 2000, that is laminar, and whenever it is greater than 4000, that is turbulent. Okay, so when we write the equation or when we see the equation rho Vd by mu, we can see that the density of the fluid, or we can consider as liquid, it is constant, and we consider the diameter of the pipe to be constant. For the Reynolds number value to be less than 2000, we say that the velocity and viscosity we are considering. Okay, so it is less than 2000 means even if we get a value of 10, it is laminar, right? Whenever we get a value of 10, it is laminar, or whenever we get a value of 100, it is also what we say, it is laminar, right? So when we consider two parameters only, that is the velocity and viscosity, at what condition do we get a flow to be laminar or the Reynolds number value to be much less? We can say that it occurs at low velocity and at high viscosity, right? When the numerator value is low and the denominator value is high, usually the number you are getting is very low, comparatively very low. So we can say that for the flow to be laminar, the condition that usually considered is low velocity and high viscosity, right? Now if we consider the flow to be turbulent, which is greater than 4000, so it can become 1 lakh, it can become 10 lakh, it can become 10,000, whatever it can be. So for that much higher value, what will be the condition of velocity and viscosity? It is the opposite of this, right? So the numerator should increase and the denominator should decrease, which means turbulent flow occurs at high velocity and low viscosity. You can expect some theory questions from this scenario. Maybe which of the statements are correct or incorrect, something like that. So remember, laminar flow occurs at high viscosity and low velocity, and for turbulent flow it is the reverse. So sometimes, or when we say about laminar flow, it is also known by another name, which is also called viscous flow. So remember, laminar flow is also known as viscous flow, okay, because it occurs at high viscosity. In this scenario, which means when we are discussing about major laws, we are assuming that, remember, we are assuming that the flow is turbulent. We are assuming that the flow is turbulent and the pipe is running full. These two assumptions are considered while we discussing about major laws or for any scenario in case of flow through pipes. The flow is turbulent and the pipe is running full. So you can probably ask, Why we assume that the flow is turbulent? Can it be viscous or laminar? It can be. So in that also there are separate equations. Maybe you know the name Hagen-Poiseuille equation. That equation is when we are considering the flow to be laminar. So in this section we are considering about major laws. We are considering the flow to be turbulent and it is running full. Clear? Okay. Now the losses we are classifying, which means whenever a flow occurs in a pipe from any section to another section, there will be losses. There will be losses. So losses we can classify into two. One is major loss and the second one is minor loss. So from the name itself we can understand that the major loss contribute to the majority of the losses and the minor loss, the percentage is comparatively very less, right? So major loss, what is the reason? There is only one reason. There is only one reason for major loss and it is due to friction or friction alone. Major loss is only due to friction. On the other hand, when we discuss about minor loss, it is due to the change in magnitude or direction of velocity. Due to the change in magnitude or direction of velocity. Okay. So today in this session we are discussing about only the major loss. What is the formula for finding the major loss? What are the equations? What are the terms that are used? All these things. Okay. For finding the major loss, the equation that is commonly used is, I think you know the name or you heard the name. The equation is known as Darcy-Weisbach equation. So remember, this equation is used to find the major loss or the friction loss in a pipe which is running full and the flow to be turbulent. These two conditions are mandatory for applying Darcy-Weisbach equation. Okay. Now, there is one more equation that is we are not commonly known. It is also used, just remember that that equation is also used or that equation can be used, but the preferred one is always Darcy-Weisbach equation. You can also use Chezy's equation. You can also use Chezy's equation for finding the major loss or friction loss. When you hear about Chezy's equation, you think about open channel flow, right? For finding the velocity and all those stuffs. But remember that main function is all of Chezy's equation is used in open channel flow, but it can also be used in pipe flow for finding the major loss or the friction loss. Okay. Today we discuss about these two equations. Now first discuss about this the commonly used one, which is Darcy-Weisbach equation. Okay. So I am considering a pipe. Let the diameter of the pipe to be constant, or we are assuming that the pipe diameter is uniform. So this is section 1 and this is section 2. Let D be the diameter of the pipe and L be the distance or the length between the two sections and V be the velocity of flow. Let V be the velocity of flow. So when the flow from 1 to 2 occurs, there is a loss due to friction because the surface of the pipe is rough or the walls of the pipe is rough, so there is a major loss. And the equation for major loss according to Darcy-Weisbach equation is given as HF is equal to 4FL V square divided by 2GD. 4FL V square divided by 2GD. This is a very important equation. This equation is very, very important. In this, L is the length of the pipe, V is the velocity of flow, D is the diameter of the pipe, and HF means friction loss or the head loss due to friction. Okay. What about F? Many of the students have a confusion. Why is it written like this? 4 and 2 like this. It can be easily be cut to be like this. It is more easier. 2FL V square by 2GD. It is not like that because in this formula there is also a modification that I will say next. So now let us say in this equation 4FL V square by 2GD, what actually is F? F is known as, in this equation F is known as coefficient of friction, or it is also known by the name friction coefficient. Okay, friction coefficient, or it is also known as coefficient of friction. Okay, in this formula for FL V square by 2GD, F is known as coefficient of friction or friction coefficient. Okay, Now, this equation can also be modified to another form. That is what I said earlier. This equation can also be modified to another form like this. You can use a different f. Now, I am using small letter f for this friction coefficient or coefficient of friction. In the other equation, I am using capital F. So, this can also be written like this. FL V square by 2GD. FL V square by 2GD. Here, F is known as friction factor. Remember, here F is known as friction factor. So, when we compare these two equations, we can easily understand the relation between friction factor and coefficient of friction. What will be it? It will be 4F is equal to capital F, which means 4 times the coefficient of friction will be equal to the friction factor. Okay, so this is the equation. Now, understand one more thing. This is not actually Darcy-Weisbach equation. Maybe we have studied in our college in fluid mechanics that this equation is like this, but there is a slight change. The actual equation is written like this. HF is equal to 4FL V raised to N divided by 2GD. Actually, this is the actual equation for finding the friction loss due to, according to Darcy-Weisbach equation, where the value of N varies between 1.5 to 2. Remember, the value of N can vary from 1.5 to 2. Then why this equation is studied like this? This is mainly because for the easiness of calculation, it is easy to do the square rather than 1.5 or 1.6 or 1.7, right? So, for the easiness of calculation, the value of N is generally approximated to 2. But you always have to remember, when you are preparing for GATE exam, you also have to remember that the value of N is not actually 2. The value of N can vary from 1.5 to 2, and for the easiness of calculation, we are approximating the value of N to 2. Okay. Now, this equation can also be written in terms of discharge. This is in the form of velocity. This equation can be written in terms of discharge. You have to study both the equations. That means one equation in terms of velocity and one equation in terms of discharge. Why I am saying this is, when we move further in this chapter, there will be a topic which is known as pipe connections. There will be series connection and parallel connection. So, in most of the scenario, we cannot keep the velocity to be a constant, but we can able to make or keep the discharge constant that usually we get from where? Continuity equation. So, you have to study one equation in terms of discharge also. How we will convert? We know that from continuity equation or from the equation of discharge, Q is equal to area into velocity, right? So, here we are having velocity. So, we convert velocity like this, Q divided by area. The pipe is circular, so the diameter is D, so Q into 4 divided by pi D square, right? This will be our velocity. So, in the main equation, that is 4FL V square by 2GD, we will substitute the value of V as Q by pi D square into 4. So, when you substitute this, we will get HF is equal to 4FL V square, right? So, Q square into 4 square divided by pi square G D raised to 5 into 2, right? Okay. So, 4 square is 16, 16 into 2 is 32, and we get the friction loss in terms of discharges 32 AFL Q square by pi square G D raised to 5. This is the equation for friction loss in terms of discharge. Now, this is where F is coefficient of friction. Now, let's substitute with friction factor. So, it will be like this, right? So, 32 divided by 4 we get 8. So, we can write HF as 8FL Q square by pi square G D raised to 5. Maybe you have not seen this equation. This equation is further modified like this. You know the value of pi square, right? It is something like 9.86 and g value is 9.81. So when you divide 8 with this value, we can get a modified version of this equation which you have commonly seen like this: FL q square by 12.1 g d raised to 5. So you have 4 equations. 2 equations in terms of discharge, 2 equations in terms of velocity, 2 equations in terms of friction factor, 2 equations in terms of coefficient of friction. You have to study only 2 equations because studying a number of equations won't help. So whenever you study major laws, you have to study 2 equations. One equation must be in terms of velocity and the other equation must be in terms of discharge, because as I already said, when we move along, when we consider or when we study about the connections, we have to make the discharge at some point constant, because usually we can make discharge constant rather than making the velocity to be constant. Clear? So these 4 equations you have to study. It is better you study 2 equations. Now, moving further into this topic, it has been said that the coefficient of friction, like the coefficient of friction F, is a function of Reynolds number. Is a function of a Reynolds number. Which means if your flow is laminar, your coefficient of friction is 16 divided by Re. If your flow is laminar, 16 divided by R if the flow is laminar. And if the flow is turbulent, the coefficient of friction is written like this: 0.079 divided by Re raised to 1 by 4. If the flow is turbulent, but there is an upper limit, which means the value should be greater than 4000, but it should be less than 10 power 6. Then only you can use this equation like this: 0.079 divided by Re raised to 1 by 4. When we study turbulent flow in detail, this equation can be further analyzed. That I will say in that section. Okay. Now just you understand that for the flow to be laminar, or if the flow is laminar, the coefficient of friction is 16 divided by Re, and if the flow is turbulent, it is 0.079 divided by Re raised to 1 by 4. This is Darcy-Weisbach equation for finding the major loss or the friction loss. Okay. Now we have one more equation. The equation is Chezy's equation. So Chezy's equation again most widely used in terms of open channel flow, but here also we can use this equation, right? Just I am saying that. So from Chezy's equation we write the formula like this: C, or velocity V, is equal to C root Mi. V is equal to C root Mi. C will be Chezy's constant. C will be Chezy's constant. M will be hydraulic mean depth, or it is also known as hydraulic radius. Hydraulic mean depth or hydraulic radius. What actually is M, or what actually is hydraulic mean depth or hydraulic radius? It is given us as the ratio of wetted area, wetted cross-sectional area, your wetted cross-sectional area divided by wetted perimeter. This is actually hydraulic mean depth or hydraulic radius. Okay, so wetted cross-sectional area, what will be the formula? Your pipe is circular, the diameter is d, and we have assumed that the pipe is running full. So what will be the cross-section that will be wetted? The whole cross-section area, right? So we can say that in this case M is pi by 4 d square, which is your cross-sectional area, and pi d is your perimeter. When we strike off these two values, we get the value as d by 4. This is your M, hydraulic mean depth or hydraulic radius. Now we need I, right? I is the hydraulic gradient. I is known as the hydraulic gradient, and I is obtained by using the formula HF by L. Actually, we have written this formula for finding the friction loss, right? So when we write this formula, V is equal to 0 to Mi, there is no term indicating friction loss, right? But we closely analyze, we get that I is known as the hydraulic gradient, and hydraulic gradient is written by the formula HF by L, which is the head loss per unit length, or the head loss due to friction per unit length. So you substitute this formula, you get the values, you substitute all these values, you calculate, and you can find the value of HF using Chezy's equation. Even though we are having two equations, the most commonly or the most preferred equation is always Chezy's, no, Chezy, it's not Chezy, it is Darcy-Weisbach equation. Okay, so this is the topic, major laws. Now let's discuss one previous year problem that has been asked from this major laws topic. So this is the question. This is asked in 2017 GATE exam and the weightage of this question was 2 marks. Okay, so it is very easy when we compare GATE exam. So you can just read the question and try to solve. So the question is like this: water is pumped at a steady uniform rate of 0.01 meter cube per second through a horizontal smooth circular pipe of 100 mm diameter. It is given that the Reynolds number is 800 and the question, or we have to find the head loss per kilometer length due to friction. Remember, they have not asked head loss, they have asked head loss per kilometer length and it is due to friction. Okay, so we write, or we know the equation like this, right? HF, and the quantity that is given is 0.01 meter cube per second, and we know that the unit of discharge is meter cube per second, so discharge is also known as rate of flow. Okay, so the discharge is given as Q is given as 0.01 meter cube per second. Then the diameter of the pipe is 100 mm. You have to convert it into a convenient unit. It is better to convert into meter, so it is 100 into 10 raised to minus 3 meter. Then the Reynolds number is given as 800 and we have to find the head loss per kilometer length. Okay, so now let's write the equation of HF in terms of discharge. So the equation is HF is equal to FLQ square divided by 12.1 D raised to 5. This is the equation. Okay. Now we require the head loss per kilometer length, which means we require the head loss per length. So we rearrange this equation like this. So we need HF by L, that is equal to FQ square divided by 12.1 D raised to 5. Right? So we already have Q and D, but we do not have F, which is a friction factor. For finding the F, they have given us Reynolds number as 800. We know that if the flow is laminar, the Reynolds number value is less than 2000. So for the flow to be laminar, the coefficient of friction is given as 16 divided by Re, right? So what will be the formula for friction factor? It is 4F, right? So it is 64 divided by Re. So you put 64, you divide by 800, you can divide it with 8, so it will be like 8 8s are 64, it is 100, and your value you are getting is 0.08. Okay, that is your friction factor. Now you substitute F as 0.08 into your discharge is 0.01 cumex, so or meter cube per second, so it is 0.01 square, and it is 12.1 into D raised to 5, it is 100 into 10 raised to minus 3, which is equal to 0.1 meter, right? 100 into 10 raised to minus 3 is 0.1 meter, so it is 0.1 raised to 5. 0.1 raised to 5. So all these values are 1.08, 12, 0.1 you have a calculator and you can solve it, and when you solve it you get the answer like this. It will be 0.06611 meter per meter length. So there is no negative mark because it is a blank, there is no options, but they have not asked this value. You have to read the question. They have asked what is the head loss per kilometer length. We got the head loss per meter length. So we have to find the head loss per kilometer length. For that, what we have to do? Tell what we have to do. We have to divide per kilometer length divide by 1000, which means it will be like this: 0.00611 meter per kilometer length, but you have to divide by 1000. You have to divide by 1000. That is, it is meter. So you have to find it kilometer. You have to divide that denominator by again 1000. What happened to this 1000? This become the numerator, and your answer will be. So this again, this is what actually we got. It is 0.61, right? So it is 0.611 and your answer will be 66.11 meter per kilometer length. Okay, so this is an easy 2-mark question. Okay, so hope you understood this section, major laws. Until next time, thank you.
Start your preparations for engineering competitive exams from top educators. Learn from the best.